Right now, 63 light years from Earth, glass is falling from the sky at more than 5,000 miles per hour. Not snow, not dust, glass. The planet is called HD 189733b. From a distance, it appears as a deep blue world, calm and beautiful enough to be mistaken for an ocean planet. In reality, its atmosphere is filled with silicate particles, driven by winds moving faster than 7 times the speed of sound. And somehow, it is not the most dangerous world we know. Elsewhere in the galaxy, there is a planet where iron evaporates into the atmosphere, drifts across the sky as vapor, and falls back to the surface as liquid metal rain. Another circles its star so closely that a full year lasts less than 2 Earth days, while temperatures climb high enough to vaporize metals. Scientists have discovered worlds darker than charcoal, planets that reflect almost no light at all, despite orbiting blazing stars. They have found rogue planets wandering through interstellar space without a sun, drifting alone through darkness that has lasted for billions of years. And they have identified planets that are actively being destroyed, their atmospheres stripped away by the stars they orbit, their final moments already underway. What makes these places unsettling is not that they belong to science fiction. They do not. Every one of them is real. Every one has been detected, measured, and studied using published observations gathered by some of the most sophisticated instruments humanity has ever built. Over the last few decades, astronomers have confirmed more than 5,700 planets beyond our solar system. Many are strange, some are difficult to explain, and a handful are so extreme that they force scientists to rethink how planets can form and survive in the first place. The universe, it turns out, is remarkably good at creating worlds that were never meant to be lived on. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. To understand how we discovered these worlds at all, we need to start with the challenge of finding planets we can never visit. Long before we arrive at any of these distant worlds, there is a small challenge waiting for us. Every planet in this journey lies far beyond the reach of spacecraft, beyond the reach of human footsteps, and beyond anything you could ever see with your own eyes. Yet somehow, we know they are there. The first clue often arrives as a tiny flicker. A planet passes between its star and us, blocking a fraction of the starlight for a brief moment. Astronomers call this the transit method. It is remarkably simple in principle and extraordinarily powerful in practice. When the Kepler Space Telescope began observing the sky in 2009, it watched roughly 150,000 stars at the same time, searching for these repeating dips in brightness. A small shadow became evidence of an unseen world. Some planets reveal themselves differently. Instead of crossing in front of their star, they pull on it. Gravity works both ways. As a planet circles its star, the star responds with a subtle motion of its own, shifting back and forth through space. This movement changes the color of the star's light by tiny amounts. Astronomers measure those changes using a technique called radial velocity, which simply means tracking motion toward or away from us through light itself. Occasionally, we manage something even more difficult. We photograph a planet directly. This approach is known as direct imaging. The challenge is immense. A star can outshine its planets by millions or even billions of times. To glimpse the faint world nearby, astronomers use a device called a coronagraph, which blocks much of the star's glare. Only a small number of exoplanets have ever been captured this way. Most remain hidden within the brightness of their suns. But perhaps the most remarkable technique asks a deeper question. What are these worlds actually made of? When starlight passes through a planet's atmosphere, Certain colors are absorbed by specific gases. This process, known as transmission spectroscopy, allows scientists to identify atmospheric ingredients without ever touching the planet itself. A missing fingerprint of light can reveal water vapor. Another may indicate methane. Others point toward carbon dioxide. Chemistry announces its presence across unimaginable distances. The Kepler Space Telescope transformed this field before retiring in 2018, contributing more than 2,600 confirmed planetary discoveries. Soon after, the transiting exoplanet survey satellite continued the search, focusing on nearby bright stars scattered across the sky. New targets emerged, new mysteries followed. Now, the James Webb Space Telescope extends that reach even further. Its powerful infrared instruments can examine planetary atmospheres with extraordinary sensitivity, detecting molecules and tracing environmental conditions that were once completely beyond our grasp. Everything we discuss from this point onward begins with real measurements: curves of light, shifts in color, gravitational motions, thin slices of filtered starlight. That may be the most astonishing part. Most of these distant worlds first appeared as little more than a shadow, a wobble, or a faint spectral signature. From those delicate signals, scientists reconstructed oceans of lava, storms of glass, iron rain, and planets wandering alone between the stars. The universe whispers, and we learn to listen. Among the thousands of worlds now known beyond our solar system, few disguise themselves as convincingly as this one. If you could view it from afar, suspended against the darkness of space, you might mistake it for something familiar. Its color is rich and blue. Its appearance feels strangely welcoming. That impression would not survive long. We find this planet in the constellation Vulpecula, roughly 63 light years from Earth. It carries the name Hotel Delta 189733b. From a distance, its blue atmosphere resembles the colors of Earth or Neptune, but the source of that color is entirely different. There are no vast oceans beneath those clouds. Instead, the atmosphere contains tiny silicate particles, the same basic material found in glass. The result is beautiful. The environment is lethal. This world belongs to a class known as a hot Jupiter, a gas giant orbiting extremely close to its parent star. It is roughly 13% larger than Jupiter itself, yet circles its star at only about 1/30th of the distance separating Earth from the Sun. Its year lasts just over 2 Earth days. Seasons never have time to form. Heat dominates everything. The side facing the star reaches approximately 1000 degrees Celsius or 1832 degrees Fahrenheit. At such temperatures, ordinary assumptions about weather begin to break apart. The planet is tidally locked, meaning one hemisphere permanently faces its star, while the opposite side remains turned away. This creates a tremendous temperature contrast across the globe. Air responds violently. Atmospheric currents race from one hemisphere toward the other at speeds approaching 8,700 kilometers per hour, which is about 5,406 miles per hour. These winds travel at roughly 7 times the speed of sound on Earth. Nothing comparable exists anywhere in our own planetary system. Within those rushing currents, the silicate particles condense into tiny fragments of glass. They gather in the atmosphere and are carried sideways by the powerful winds. Rain still falls here, in a sense, but it does not descend gently from overhead. It moves horizontally across the planet at extraordinary speed. Imagine weather becoming a weapon. Any object exposed to those conditions would face a relentless barrage of fast moving glass particles. The atmosphere itself becomes abrasive, sculpted by heat and motion into something both dynamic and destructive. Yet this planet holds an important place in astronomical history beyond its dramatic appearance. In 2007, it became the first exoplanet whose atmosphere was studied directly in significant detail. Researchers detected sodium and water vapor, later identifying carbon dioxide and methane as observational techniques improved. Knowledge advanced quickly. Then, in 2013, astronomers from the University of Oxford used observations from the Hubble Space Telescope to confirm the planet's deep blue color. What seemed at first like a visual curiosity became a valuable scientific laboratory. Methods refined here would later be applied elsewhere. As we examine distant atmospheres today, searching for clues about planetary environments, many of those techniques trace part of their development back to this remarkable blue world, where beauty and danger share the same sky. Far out in the constellation Pisces, a strange cycle unfolds without pause. Material rises, travels across a planetary sky, cools, and falls again. On Earth, that cycle belongs to water. Here, it belongs to metal. We arrive at a world known as WASP 76b, located approximately 640 light years away. It is an ultra hot gas giant, swollen by intense heat and locked in a close embrace with its parent star. One side faces perpetual daylight, the other remains turned away. Between them lies a boundary where two radically different environments meet. The day side is astonishingly hot. Temperatures climb to roughly 2,400 degrees Celsius or 4,352 degrees Fahrenheit. Under such conditions, familiar distinctions begin to disappear. Rocks behave differently. Chemistry changes. Even metals can no longer remain solid. Iron becomes vapor. In March of 2020, a research team led by David Ehrenreich at the University of Geneva published an extraordinary result in the journal Nature. Using the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations mounted on the Very Large Telescope in Chile, they examined the planet's atmosphere in remarkable detail. What they found was unexpected. Iron vapor appeared clearly near the evening side of the planet, where daylight gives way to darkness. Yet the same signal was missing near the morning side, where darkness returns to daylight. The imbalance demanded an explanation. The answer seems to involve weather unlike anything known in our solar system. On the blistering day side, iron is heated until it enters the atmosphere as vapor. Powerful winds then carry that vapor across the planet. When the material reaches the cooler hemisphere, temperatures fall enough for condensation to occur. Cooler is a relative term here. Conditions may still hover around 1,500 degrees Celsius or 2,732 degrees Fahrenheit. Even so, it is sufficient. The vapor transforms once again. Droplets form. Gravity takes over. Molten iron begins to fall through the atmosphere in a metallic rainstorm. Sunset means something different here. Instead of relief from heat, the transition toward darkness may bring streams of liquid metal descending from above. The entire process is driven by the planet's tidal locking, a state where one hemisphere permanently faces the star while the opposite side remains in darkness. That contrast powers immense atmospheric motion. Jet streams race around the equatorial regions, transporting heat and material across the globe. Alongside iron, astronomers have identified sodium, calcium, lithium, hydrogen, and manganese within the atmosphere. Each detection adds another piece to the portrait of this extreme environment. Scale matters as well. WASP 76b measures roughly 1.8 times the diameter of Jupiter, yet it is less dense than Jupiter, inflated by the constant energy pouring into its atmosphere. The planet has expanded under relentless heating, becoming larger and more diffuse than its mass alone would suggest. As we observe this distant world, we witness an active planetary system reshaping itself through temperature, motion, and chemistry. Metal evaporates, winds transport it, gravity returns it to the depths below. The cycle continues, unbroken beneath an alien sky. Temperature usually helps us distinguish stars from planets. One glows through nuclear fusion, the other reflects or re radiates energy received from elsewhere. For most worlds, that boundary remains clear. Then we encounter Kelt 9b. This planet resides about 670 light years from Earth within the constellation Cygnus. At first glance, it appears to be another gas giant orbiting close to its star, but closer examination reveals something extraordinary. Its dayside temperature reaches approximately 4,300 degrees Celsius, or 7,772 degrees Fahrenheit. That number changes everything. Most planets never approach such conditions. Kelt 9b is hotter than the surfaces of many stars scattered throughout the Milky Way. For comparison, the visible surface of our Sun measures roughly 5,500 degrees Celsius, or 9,932 degrees Fahrenheit. The difference between them is surprisingly small. You are no longer comparing a planet to Earth. You are comparing a planet to a star. The source of this intense heating is its parent star Kelt 9, a brilliant blue-white stellar giant. This star is roughly twice as hot and approximately 2.5 times more massive than our Sun. Kelt 9b circles astonishingly close to it, completing a full orbit in only 1.48 Earth days. Distance offers little protection. Radiation pours across the atmosphere with relentless intensity. Among the most destructive forms is ultraviolet radiation, energetic light capable of breaking apart molecules and reshaping entire atmospheres. On Kelt 9b, that process is underway right now. The planet is actively losing material to space. Its atmosphere is eroding. Ordinary molecules struggle to survive under such conditions. Hydrogen molecules, which normally consist of two hydrogen atoms joined together, are torn apart by the heat on the day side. Individual atoms drift through the atmosphere. Some may recombine later after reaching cooler regions, creating a cycle driven entirely by extreme temperatures. Chemistry becomes unstable. Observations have revealed ionized iron and ionized titanium, atoms stripped of electrons by intense energy. Astronomers have also detected hydrogen, sodium, magnesium, chromium, and scandium. The resulting chemical signature resembles the atmosphere of a star more than that of a conventional planet. That distinction matters. Planetary atmospheres usually contain stable molecules and compounds. Here, many substances exist in altered states because the environment is too energetic for normal chemical balance. Kelt 9b occupies a strange middle ground where planetary and stellar characteristics begin to overlap. Its discovery carries another surprise. In 2017, astronomers identified this remarkable world through the Kilodegree Extremely Little Telescope survey. Despite its imposing name, the project relied on relatively small and inexpensive instruments. One of the most extreme planets ever found emerged from one of the most modest observing systems. Meanwhile, the planet continues to change. Models suggest atmospheric escape may persist for immense spans of time. As material streams away, Kelt 9b could eventually lose much of its gaseous envelope. What remains may be a dense core exposed beneath the layers that once surrounded it, a transformed remnant shaped by heat beyond ordinary planetary limits. Most worlds announce themselves by reflecting starlight. Even from enormous distances, a planet usually gives something back, a glimmer, a brightness, a trace of illumination that reveals its presence. TRES 2b does the opposite. Light reaches this planet and largely disappears. Located approximately 750 light years away in the constellation Draco, TRES 2b holds a remarkable distinction. It is the darkest planet ever measured. Less than 1% of the light striking its atmosphere returns to space. By comparison, Earth's clouds, oceans, and ice reflect roughly 30% of incoming sunlight. Our moon reflects about 12%. TRES 2b reflects almost nothing. Its darkness exceeds that of coal. It surpasses black acrylic paint. No known planet or moon in our own solar system absorbs light so completely. When astronomers first began studying this world, the measurements seemed almost implausible. Yet the data remained consistent. The planet was originally discovered in 2006 through the Transatlantic Exoplanet Survey. Several years later, observations from the Kepler Space Telescope allowed researchers to determine just how little light the planet reflected. In 2011, the picture became clearer. TRES 2b was not merely dark, it was extraordinarily dark. That finding created a puzzle. The planet belongs to the hot Jupiter family, orbiting extremely close to its star. Its atmospheric temperature reaches approximately 1,100 degrees Celsius, or 2,012 degrees Fahrenheit. It circles only about 5 million kilometers from its parent star, which is about 3,107,000 miles. For comparison, Mercury orbits roughly 58 million kilometers from the Sun, which is about 36,038,000 miles. Heat floods the atmosphere. The planet is also thought to be tidally locked. One hemisphere continually faces its star, while the opposite side remains turned away. Under those conditions, astronomers expected a bright atmosphere containing reflective clouds, but observations revealed the opposite. Something is swallowing the light. Several explanations have been proposed. Vaporized sodium and potassium may absorb large amounts of incoming radiation. Another possibility involves titanium oxide gas suspended high in the atmosphere. These substances can act like atmospheric pigments, trapping light before it has any chance to escape. Yet, uncertainty remains. Other hot Jupiters possess similar temperatures and broadly similar compositions. Most do not exhibit this extreme darkness. TRES 2b behaves differently, suggesting that some unique combination of chemistry, atmospheric structure, and circulation is at work. Even so, the planet is not entirely black. At temperatures exceeding 1,000 degrees Celsius, or 1,832 degrees Fahrenheit, the atmosphere likely emits a faint reddish glow of its own. The effect would resemble a smoldering ember viewed from afar, producing light through heat rather than reflection. That detail makes the mystery even stranger. A world immersed in stellar radiation should shine more brightly than this. Instead, TRES 2b absorbs nearly everything offered to it. More than a decade after its darkness was measured, astronomers still lack a complete explanation. Among the many exotic planets now known, this one remains a genuine atmospheric riddle hidden behind a veil of missing light. Some planets become famous long before we truly understand them. A single possibility captures public imagination, spreads through headlines, and settles into memory. 55 Cancri E is one of those worlds. Its reputation began deep beneath the surface. Located only 41 light-years away in the constellation Cancer, this super-Earth ranks among the nearest known rocky exoplanets. It is roughly twice Earth's diameter and carries about 8 times Earth's mass. Yet despite its size, the most striking feature may be the astonishing speed of its orbit. The planet races around its star. One complete year lasts only 17 hours and 41 minutes. When astronomers announced its discovery, no known planet orbiting a sun-like star completed an orbit more quickly. The world circles so close to its parent star that conditions on the day side become extreme. Temperatures soar. Surface estimates reach approximately 2,000 degrees Celsius or 3,632 degrees Fahrenheit. At such heat, rock itself approaches a molten state. Landscapes, familiar to us, lose meaning. Mountains, plains, and solid ground become uncertain concepts. Then came a remarkable proposal. In 2012, astrophysicist Niku Madhusudan and colleagues at Yale University suggested that the planet might contain enormous quantities of carbon-rich material. If its interior possessed far more carbon than oxygen, immense deposits of diamond and silicon carbide could exist deep below the surface. The idea attracted global attention. A planet of diamonds sounded almost mythical, yet the hypothesis emerged from genuine scientific analysis of the available data. Researchers were attempting to understand the composition of a world unlike anything in our own solar system. But science rarely stops at first impressions. By 2016, additional studies examined the chemical makeup of the host star with improved measurements. Those results suggested the system may contain less carbon than previously believed. The diamond-rich interpretation became less certain. The picture grew more complicated and more interesting. Instead of a simple answer, 55 Cancri E became an example of how planetary science evolves as observations improve. Each new dataset refined the story rather than ending it. Recent discoveries pushed that process even further. Observations from the James Webb Space Telescope in 2024 detected an atmosphere containing carbon dioxide and carbon monoxide. This marked the first confirmed atmosphere around a rocky exoplanet, a significant milestone in the study of distant worlds. The atmosphere itself may originate from below. Many researchers now favor a lava world scenario. The dayside could be covered by a vast ocean of molten rock, continuously releasing gases into the atmosphere. In this view, the planet behaves like a giant geological engine, reshaping its surroundings through heat and volcanic activity. Evidence supports that possibility. Thermal mapping has revealed dramatic temperature variations across the planet. Those changes suggest an environment that may shift over time, perhaps through large-scale volcanism or evolving atmospheric circulation. You can even find its star in the night sky. The planet remains invisible without specialized instruments, but the host star, 55 Cancri, can be seen with the unaided eye under favorable conditions. Somewhere around that distant point of light circles a world that has repeatedly challenged expectations. Each observation adds another layer. What began as a possible diamond planet now stands as a reminder that the universe often proves more intricate than our first explanations. On Earth, weather begins with water. Oceans evaporate, clouds form, and rain returns moisture to the surface. The cycle feels so familiar that it is easy to assume weather must always work that way. Korot 7b suggests otherwise. Here, the ingredients are entirely different. Discovered in 2009 by the Convection, Rotation, and Planetary Transits mission, Korot 7b became one of the first confirmed rocky exoplanets ever identified. It orbits a star in the constellation Monoceros, approximately 489 light-years from Earth. Although only about 1.6 times Earth's diameter and roughly 7.4 times Earth's mass, This planet occupies an environment unlike anything found in our solar system. Distance is the key. Co-Rot 7b circles its star at only about 2.5 million kilometers, which is about 1,553,000 miles. One complete orbit takes just 20.4 hours. A year passes in less time than a single day on Earth. The star never feels far away. Its radiation floods the dayside with extraordinary energy. Temperatures are estimated to reach roughly 2,500 degrees Celsius or 4,532 degrees Fahrenheit. Under such conditions, familiar rocks cannot remain stable. Minerals melt, some begin to vaporize. Solid ground becomes part of the atmosphere. Researchers Bruce Fegley and Laura Schaefer of Washington University in St. Louis explored what such a world might look like. Their work described a remarkable possibility. On the scorching hemisphere, rock evaporates and rises into the sky as vapor. That vapor forms an atmosphere composed of material normally found beneath our feet. Then motion takes over. Winds transport the vapor toward cooler regions. As temperatures decline, the material condenses once again. Instead of water droplets forming clouds, mineral particles emerge from the atmosphere. Pebbles and rocky fragments fall back toward the surface. It is weather built from stone. The atmosphere itself, if present, would bear little resemblance to Earth's. Nitrogen and oxygen would not dominate. Instead, astronomers expect vaporized sodium, potassium, silicon monoxide, and other gases derived directly from molten rock. Every component reflects the planet's extreme conditions. Its history may be equally dramatic. Some scientists suspect Corot 7b did not always appear as it does today. Long ago, it may have possessed a much thicker envelope of gas, perhaps resembling a small gas giant or a Neptune-like world. Over time, intense stellar radiation could have stripped those outer layers away, exposing the dense rocky interior beneath. The planet remains under constant stress. Orbiting so closely creates powerful tidal forces. These forces stretch and compress the planet as gravity pulls unevenly across its structure. Internal friction generates heat, potentially driving widespread volcanism and geological activity. Such a world changes our definition of rock itself. We often imagine stone as permanent and unchanging. Corot 7b reveals another possibility. Under sufficient heat and pressure, rock can melt, evaporate, circulate through an atmosphere, and return again to the surface. What appears solid becomes mobile. What seems permanent becomes part of a cycle. On this distant world, geology and weather merge into a single process. The story begins with a discovery that arrived earlier than anyone expected. Before astronomers found planets around ordinary stars, before the modern age of exoplanet exploration truly began, another set of worlds emerged from the data. They were orbiting a dead star. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the first confirmed planets beyond our solar system. The finding was historic, yet the setting was deeply unusual. These worlds did not circle a warm, stable star. Instead, they orbited an object known as a pulsar. A pulsar is the collapsed core left behind after a massive star explodes as a supernova. The original star is gone. What remains is a neutron star, an object so dense that a spoonful of its material would outweigh mountains on Earth. This particular pulsar, designated PSRB 1257 plus 12, lies about 2,000 300 light years away in the constellation Virgo. It spins with astonishing speed. The neutron star rotates approximately 161 times every second. As it turns, powerful beams of radiation sweep outward into space. When those beams cross Earth's line of sight, astronomers detect regular pulses, creating the appearance of a cosmic beacon flashing through the darkness. Around this remnant world, 3 planets have been confirmed. Their names are Draugr, Poltergeist, and Phobator. Draugr possesses only about 2/100ths of Earth's mass, making it one of the lowest mass exoplanets known. Poltergeist carries roughly 4.3 Earth masses. Phobator follows closely behind at about 3.9 Earth masses. The names feel appropriate. Each comes from legends associated with spirits, apparitions, or the restless dead. These worlds circle the remains of a star that no longer shines in the ordinary sense, existing within one of the harshest environments yet discovered. Radiation dominates everything. Pulsars emit intense beams across the electromagnetic spectrum, including energetic X rays and gamma rays. Any planetary surface exposed to this bombardment would endure conditions far beyond the limits of known biology. Atmospheres would struggle to survive. Complex molecules would be broken apart. Life as we understand it would face overwhelming challenges. Yet another mystery remains. How did planets end up here at all? One leading explanation proposes that these worlds formed after the supernova itself. Material left behind by the stellar explosion may have settled into a disk of debris surrounding the neutron star. Over time, particles collided, accumulated, and eventually assembled into planets. If this idea is correct, these worlds were born directly from the wreckage of a destroyed sun. But another possibility exists. The planets may have originated elsewhere, perhaps around a companion star that later interacted with the pulsar. Through a complex gravitational history, they could have been captured and retained after dramatic stellar evolution reshaped the system. Either scenario carries profound implications. The first confirmed exoplanets ever discovered were not orbiting a familiar stellar environment. Humanity's introduction to other worlds came through planets circling a stellar corpse, reminding us that planetary systems can emerge in places far stranger than early astronomers ever imagined. Every planet we have visited so far shared one thing in common. Somewhere nearby, a star provided light, heat, and a gravitational anchor. Rogue planets break that pattern completely. They travel alone. A rogue planet, sometimes called a free-floating planet, drifts through interstellar space without orbiting any star. There is no sunrise waiting beyond the horizon, no seasonal cycle, no parent sun marking the passage of years. These worlds move through the vast regions between stellar systems, untethered and largely unseen. Their origins remain varied. Some likely formed within ordinary planetary systems before violent gravitational encounters hurled them into space. A close interaction with a giant planet or passing star can dramatically alter an orbit. Occasionally, the result is complete ejection. A world that once belonged somewhere suddenly finds itself wandering the galaxy. But that is not the only possibility. Some rogue planets may have formed independently within collapsing clouds of gas and dust, following a path more similar to star formation than traditional planet formation. In that case, they may have spent their entire existence alone. Astronomers suspect there are many of them. A study published in Nature during 2011 suggested that rogue planets could number in the billions within the Milky Way alone. Some estimates even imply that they may outnumber stars. Later observations strengthened the possibility. In 2021, Researchers examining data from the optical gravitational lensing experiment and the Young Upper Scorpius Stellar Association identified between 70 and 170 rogue planet candidates within a single region of the sky. The population may be enormous. Conditions on these worlds are difficult to imagine. Without the warmth of a nearby star, surface temperatures could fall toward negative 270 degrees Celsius or negative 454 degrees Fahrenheit. That is only a few degrees above absolute zero, the coldest temperature physically possible. The surface would freeze completely. Yet some scientists suspect that warmth may survive deep below. Radioactive elements within the core continue to release energy over immense spans of time. Residual heat from planetary formation can also linger. If sufficient heat remains trapped beneath thick layers of insulating ice, liquid water might persist underground. An ocean hidden from space. Could life exist in such an environment? The question remains unanswered, yet it continues to attract scientific attention. On Earth, microbial life thrives around deep underground heat sources far from sunlight. Similar conditions elsewhere cannot be dismissed outright. Finding these worlds presents another challenge. Traditional exoplanet techniques depend on stars. A rogue planet does not transit a visible stellar disk, nor does it create an easily measurable stellar wobble. Instead, astronomers often rely on gravitational microlensing, a phenomenon in which the planet's gravity briefly bends and magnifies the light of a distant background star. The alignment lasts briefly, then it vanishes. Future surveys conducted by the Nancy Grace Roman Space Telescope are expected to identify many more examples. Some of those worlds may have wandered for billions of years, older than Earth and perhaps older than the Sun itself, crossing the dark expanses between stars, with no destination and no permanent companion. Some worlds challenge our sense of scale. Others challenge our sense of possibility. HAT P7b belongs firmly to the second category, a place where familiar minerals participate in weather patterns unlike anything you and I have ever known. This giant planet lies about 1,040 light years from Earth within the constellation Cygnus. It is a hot Jupiter, measuring roughly 1.4 times Jupiter's diameter, while racing around its host star every 2.2 Earth days. The orbit is astonishingly tight. There is little relief. The star itself outweighs our Sun by roughly 50% and shines with about twice the luminosity. Under that relentless radiation, the day side of HAT P7b reaches temperatures exceeding 2,500 degrees Celsius, or 4,532 degrees Fahrenheit. At such extremes, many materials behave in unfamiliar ways. Even clouds change character. For decades, astronomers could only speculate about weather on distant gas giants. Then, a remarkable breakthrough arrived during 2016. Researchers, led by David Armstrong at the University of Warwick, analyzed observations from the Kepler Space Telescope and noticed something unexpected. Bright regions within the planet's atmosphere appeared to shift position over time. The pattern moved. That movement suggested dynamic weather systems operating across the planet. Instead of a static atmosphere locked into place, HATP7b seemed to possess changing cloud formations driven by powerful winds circling the globe. But these were not water clouds. Models indicate that aluminum oxide may condense within cooler atmospheric regions. Aluminum oxide is better known as corundum, the mineral from which sapphires and rubies form. On Earth, these gemstones are treasured and collected. On HAT P7b, the same material may become part of the weather cycle itself. A strange cycle unfolds. As air circulates toward the cooler night side, corundum particles can condense into vast cloud decks. Winds then transport portions of those clouds toward hotter regions. Rising temperatures eventually evaporate the particles back into gas, dissolving the clouds and returning their material to the atmosphere. Formation and destruction continue. The process resembles a planetary breathing rhythm, though one governed by extreme heat and global atmospheric circulation. Rather than rainstorms crossing familiar landscapes, entire cloud systems composed of gemstone forming minerals may appear and vanish across a gas giant sky. But another detail deepened the mystery. The shifting bright spots observed by the Kepler Space Telescope did not remain fixed over long periods. Their positions changed, suggesting large scale storms or evolving wind patterns. The climate appeared active rather than stable. Weather on HAT P7b was not merely present, it was changing. Would you recognize such a sky? Any observer floating within those upper layers would encounter conditions far removed from earthly experience. Temperatures capable of melting rock coexist with atmospheric currents powerful enough to redistribute clouds across an entire hemisphere. Minerals associated with jewelry become ingredients in meteorology. That contrast makes HAT P7b memorable. On Earth, weather often means rain, snow, or drifting clouds. Here, weather may involve sapphire and ruby precursors forming, migrating, and evaporating beneath the glare of an intensely luminous star, revealing just how flexible nature becomes when familiar ingredients are placed in unfamiliar environments. Categories help us organize the universe. Rocky planets occupy one shelf, gas giants occupy another. Yet every so often, astronomers encounter a world that refuses to fit either description. GJ 1214 b is one of those worlds. Located about 48 light years away in the constellation Ophiuchus, this planet has become one of the most closely studied examples of a class known as a sub-Neptune, sometimes called a mini-Neptune. These planets are larger than Earth, but smaller than Neptune. Our own solar system contains nothing quite like them. That absence matters. GJ 12. 14. B measures roughly 2.7 times Earth's diameter and carries about 6.5 times Earth's mass. It circles a small red dwarf star once every 1.58 Earth days, remaining extremely close to its parent star. Yet, despite years of observation, the planet has guarded many of its secrets. The atmosphere came first. When astronomers examined starlight passing through the planet's atmosphere during transits, they expected to see clear chemical signatures. Instead, they found something surprisingly smooth. The transit spectra, measurements showing how different wavelengths of light are absorbed, appeared almost featureless. Such a result suggested that thick clouds or hazes were blocking deeper views into the atmosphere. A veil remained in place. As scientists compared the planet's size and mass, another possibility gained attention. Its density appeared lower than a purely rocky world would allow. Models suggested enormous quantities of water could be hidden within the planet's interior, but this would not be water resembling oceans, rivers, or clouds on Earth. Pressure changes everything. Far below the upper atmosphere, conditions may become so extreme that water enters unfamiliar states of matter. One possibility is a supercritical fluid, a form that behaves partly like a liquid and partly like a gas. Deeper still, water may transform into plasma, a state where atoms are stripped apart by immense energy. Researchers also predict the existence of hot ice, formerly known as Ice 7, a crystalline structure created when water is compressed under extraordinary pressure. The temperatures remain intense. Ice 7 can exist at hundreds of degrees Celsius while remaining solid because pressure overwhelms the effects of heat. On GJ 14b, internal pressures may reach thousands of times those found at Earth's surface. Familiar distinctions between liquid, gas, and solid begin to blur. But the most intriguing possibility lies deeper. If water dominates the planet's composition, there may be no true surface anywhere below the atmosphere. Instead, layers could gradually transition from vapor to fluid, from fluid to exotic compressed forms, becoming denser and stranger with depth. Descending through such a world would reveal no shoreline and no continent, only transformation. Evidence supporting this picture strengthened in 2023 when observations from the James Webb Space Telescope indicated a water-rich atmosphere with surprisingly little methane. The findings aligned with long-standing predictions that GJ 14b may indeed belong to a category unlike anything orbiting our Sunday. Its significance extends beyond a single discovery. GJ 14b reminds us that planets need not choose between rock and gas. Nature often creates something entirely different, and in this distant world, the most familiar substance on Earth may exist in forms we can scarcely picture. Some planets endure for billions of years, circling their stars with remarkable stability. Others follow a far less permanent path. WASP 12b belongs to that second category, a world whose future is already written into the gravity of its orbit. Located about 1,410 light years away in the constellation Auriga, WASP 12b is a giant planet caught in an extraordinary struggle with its parent star. At first glance, it resembles the hot Jupiters we have already encountered, but closer examination reveals something far more dramatic. The planet is swollen. WASP 12b stretches to roughly 1.8 times Jupiter's diameter, yet its density is remarkably low, comparable to balsa wood. Intense heat from the nearby star has inflated its atmosphere, creating a bloated world with an outer envelope only loosely held together by gravity. Distance becomes everything. The planet completes a full orbit in only 1.09 Earth days. That tiny orbit places it extraordinarily close to its star, exposing it to relentless radiation and overwhelming tidal forces. A tidal force is the difference in gravity across an object's body, pulling one side more strongly than the other. Over time, the distortion grows. Rather than maintaining a nearly spherical shape, WASP 12b has been stretched into an elongated form resembling an egg. Gravity from the nearby star continuously tugs at the planet's atmosphere, weakening its hold on the outer layers. But the process does not stop there. Observations from the Hubble Space Telescope revealed that material is actively escaping the planet. Streams of atmospheric gas extend outward and fall toward the star itself. In a very real sense, the star is feeding on its companion. The loss is immense. Astronomers estimate that WASP 12b sheds roughly 189 quadrillion tons of material each year. The number is difficult to comprehend, yet the consequences become clear when viewed across astronomical timescales. A planet that once formed as a massive gas giant is gradually being stripped apart. Heat accelerates the destruction. Dayside temperatures reach approximately 2,500 degrees Celsius, or 4,532 degrees Fahrenheit. Under such conditions, atmospheric gases expand and become even more vulnerable to escape. The star's gravity then captures part of that material and pulls it inward. Another clue emerged recently. Astronomers carefully tracked the timing of the planet's transits across its star over many years. In 2020, Samuel Yee and collaborators published strong evidence that the orbital period is shrinking. Each orbit appears to take slightly less time than before. The inward spiral continues. Every completed circuit brings the planet marginally closer to the star. This phenomenon, known as tidal decay, occurs when orbital energy is gradually transferred and dissipated through gravitational interactions. The orbit slowly contracts, but chemistry adds another layer to the story. Observations indicate an atmosphere unusually rich in carbon relative to oxygen. Such a chemical balance differs from many planetary environments and provides valuable clues about how the planet formed and evolved before reaching its current state. Today, WASP 12b offers something rare in astronomy. We are not simply observing a strange world, we are witnessing an active ending, a planetary death spiral unfolding in real time, one orbit at a time. Imagine arriving long after a catastrophe has ended, finding only a scarred survivor where an entire world once stood. That is the strange possibility presented by Kepler 70b, one of the most extraordinary planetary candidates ever proposed. The system centers on a subdwarf B star, a stellar remnant that has already endured a dramatic transformation. Earlier in its life, the star expanded into a red giant, swelling outward to enormous dimensions before shedding much of its outer material. What remains today is a hot, compact core, glowing after a violent period of stellar evolution. Yet, something appears to orbit it. Kepler 70b circles this remnant star once every 5.76 hours. The orbit is astonishingly tight. Few known planetary candidates travel around their stars so quickly. From the planet's perspective, the host star would dominate the sky, filling it with relentless radiation and heat. The temperatures are extraordinary. Estimates suggest surface conditions could reach roughly 6,800 degrees Celsius or 12,272 degrees Fahrenheit. That is hotter than the surface of our Sun, which reaches approximately 5,500 degrees Celsius or 9,932 degrees Fahrenheit. Rock behaves differently there. At such temperatures, ordinary geological distinctions begin to lose meaning. Minerals melt, vaporize, and radiate visible light. If these estimates are correct, the surface would glow intensely, turning the planet itself into a brilliant source of light. You would not see dark volcanic plains, you would see incandescent rock. But the most remarkable aspect may be its history. Astronomers suspect Kepler 70b was once a much larger world, perhaps a gas giant with a thick atmosphere. When the host star entered its red giant phase, the expanding stellar envelope likely engulfed nearby planets. Most worlds caught in such an event would be destroyed completely. Kepler 70b may have endured. According to one interpretation, the planet lost its atmosphere during this stellar expansion. Layer after layer was stripped away until only a dense core remained. What we observe today could be the exposed remnant of a former giant planet, reduced to its innermost structure after passing through one of the harshest environments imaginable. A neighboring companion adds another curiosity. Kepler 70c follows a nearby orbit around the same star. At their closest approach, the two worlds come within roughly 240,000 kilometers, which is about 149,000 miles, of one another. That distance is smaller than the gap separating Earth and our moon. Discovery itself proved unusual. Rather than appearing through conventional planetary transits, the signals emerged through subtle changes in reflected light and orbital behavior. Those measurements sparked considerable interest, but also debate. Some researchers remain unconvinced that the signals truly originate from planets. The discussion continues. But even with uncertainty, Kepler 70b occupies a fascinating place in planetary science. If the interpretation is correct, we are looking at a world that entered the swollen outer regions of its own star, survived the encounter, and emerged transformed. Few planetary stories involve such destruction. Fewer still involve survival afterward. Some discoveries force us to rethink familiar categories. Tress 4b is one of those worlds, a planet so swollen and diffuse that even astronomers struggled to understand what they were seeing when it emerged from the data. Located approximately 1,400 light-years away in the constellation Hercules, Tress 4b drew immediate attention after its discovery in 2007. At the time, it was the largest exoplanet ever found. Its diameter measured roughly 1.7 times that of Jupiter, yet its mass told a very different story. The planet was enormous. Its density was estimated at only about zero point 0.2 grams per cubic centimeter. That makes it less dense than cork, less dense than balsa wood, and roughly 1/4 the density of water. If an ocean large enough could somehow exist, Tress 4b would float upon it. That comparison sounds impossible. Planets are supposed to be substantial objects, compressed by their own gravity into compact forms. But Tress 4b appears stretched almost to the limits of what a gaseous world can remain. Its atmosphere extends far from its center, creating a bloated sphere that challenges standard planetary models. Astronomers call this the puffy planet problem. According to conventional calculations, a planet with Tress 4b's mass and temperature should be significantly smaller. Yet observations repeatedly showed an object inflated far beyond expectations. The discrepancy remains one of the enduring puzzles of exoplanet science. Part of the explanation may involve its environment. The planet receives intense radiation from its host star system. Energy pours into the upper atmosphere, heating the gas and causing expansion. But detailed studies indicate that radiation alone cannot account for the planet's extraordinary size. Other possibilities have been explored. One proposal involves tidal heating, where gravitational stretching generates heat within the planet's interior. Another focuses on ohmic dissipation, a process in which atmospheric winds move through magnetic fields, generating electrical currents that deposit additional energy. Researchers have also suggested enhanced atmospheric opacity, meaning heat becomes trapped more effectively and escapes less easily. Each idea contributes something. None fully solves the mystery. The uncertainty becomes even more striking when we consider the planet's outer layers. Gravity holds them only weakly. The atmosphere exists in a delicate balance between expansion and escape. A sufficiently energetic stellar event could potentially strip material away, allowing gas to drift into surrounding space. In that sense, Tress 4b seems less like a sharply defined world and more like a vast envelope of heated gas surrounding a relatively modest core. Where exactly does the planet end and empty space begin? The boundary becomes surprisingly difficult to define. But that uncertainty may be the most valuable lesson. For generations, planets appeared to fit a manageable collection of categories. Rocky worlds resembled Earth, gas giants resembled Jupiter. TRES 4b reminds us that nature rarely respects neat classifications. Somewhere in Hercules drifts a sphere so inflated that our definitions begin to blur, forcing us to reconsider what a planet can become when heat, gravity, and time interact in unexpected ways. Water usually brings certain expectations. We imagine oceans, clouds, rain, or frozen landscapes shaped by cold. Yet around a small red dwarf star, approximately 33 light years from Earth, exists a world that forces us to abandon every familiar assumption. This planet is Gliese 436b. Roughly comparable to Neptune in mass, it circles its host star once every 2.6 Earth days. The orbit is remarkably tight, so close in fact that the planet's temperature reaches approximately 440 degrees Celsius or 824 degrees Fahrenheit. Under ordinary conditions, water exposed to such heat would exist as vapor, but Gliese 436b is anything but ordinary. Deep beneath its outer layers, immense pressure transforms water into something entirely different. Planetary models indicate that large quantities of water may exist there as exotic forms known as Ice 7 and Ice 10. These are high-pressure phases of ice, crystalline structures that remain solid despite temperatures that would instantly boil water on Earth. The idea seems contradictory. How can ice survive in such heat? Pressure changes the rules. As gravitational forces compress material toward the planet's interior, water molecules are forced into tightly packed arrangements. Temperature alone no longer determines whether water remains solid. Instead, crushing pressure dominates, locking molecules into rigid crystal lattices that can endure astonishing conditions. This is sometimes called burning ice. Not because the ice is on fire, but because it exists at temperatures far beyond anything associated with frozen water in everyday experience. The phrase captures the strangeness of a substance that is both intensely hot and structurally solid at the same time. Yet, Gliese 436b offers another puzzle. Its orbit is noticeably eccentric, meaning it follows an elongated path rather than a nearly circular one. For a planet orbiting so close to its star, this is unexpected. Over billions of years, tidal forces should gradually smooth out such irregularities and produce a more circular orbit. But that has not happened. Astronomers suspect another unseen object may be influencing the planet through gravity, continually disturbing its motion. Another possibility involves a comparatively recent disruption that altered the orbit long after the system formed. Neither explanation has been confirmed completely. The surprises continue. Observations revealed a vast stream of hydrogen escaping from the planet's atmosphere. Radiation from the nearby star heats the upper layers, allowing gas to flow outward into space. The escaping hydrogen forms an enormous tail, trailing behind the planet, giving it a resemblance to a giant comet. The scale is immense. That hydrogen tail stretches millions of kilometers, which is about hundreds of thousands to millions of miles, behind the planet as it races around its star. Material is continually being lost, creating a world that is slowly shedding part of itself. Gliese 436b resists simple categories. It contains burning ice, carries a comet-like tail, and follows an orbit that challenges expectations. Each discovery adds another layer to the mystery, reminding us that the universe often combines familiar ingredients into realities far stranger than anything we would invent on our own. If you stepped outside on a clear night and searched for the nearest planetary neighbor beyond our solar system, your gaze would eventually settle toward a small red star only 4.24 light-years away. Around that star circles Proxima Centauri b, the closest known exoplanet to Earth. Its proximity makes it special. Unlike many worlds, scattered hundreds or thousands of light years across the galaxy, Proxima Centauri b exists practically next door on cosmic scales. The planet possesses a minimum mass about 1.17 times that of Earth, placing it firmly among the rocky worlds that attract intense scientific attention. At first glance, the numbers seem encouraging. Proxima Centauri b orbits within the traditional habitable zone, the region where temperatures could permit liquid water under suitable atmospheric conditions. A year there lasts only 11.2 Earth days because the planet circles very close to its host star. But the star changes everything. Proxima Centauri is a red dwarf, a class of star smaller and dimmer than our Sunday. Red dwarfs can survive for trillions of years, yet many spend much of their lives unleashing violent eruptions. These stellar flares release bursts of radiation capable of transforming the environments of nearby planets. One event drew particular attention. In 2018, astronomers observed a superflare from Proxima Centauri, estimated to be roughly 10 times more powerful than any solar flare ever recorded from our Sunday. Such outbursts are not rare exceptions. They are recurring features of the star's behavior. Each eruption carries consequences. Extreme ultraviolet radiation and energetic particles stream outward through the planetary system. Because Proxima Centauri b orbits so close to remain within the habitable zone, it receives the full force of these events. Over immense spans of time, repeated bombardment may erode an atmosphere molecule by molecule. The planet faces another challenge. Many researchers believe it is tidally locked. Tidal locking occurs when one hemisphere permanently faces the star, while the opposite hemisphere always faces away. If that is correct, one side experiences perpetual daylight, and the other remains in endless night. Could air currents transport heat between them? The answer remains uncertain. Some climate models suggest a sufficiently thick atmosphere could redistribute energy and moderate conditions. Others indicate that extreme contrasts might persist, producing a world divided between scorching and frozen regions. The surrounding stellar wind adds further complexity. Studies suggest the particle flow from Proxima Centauri may be as much as 2,000 times stronger than the solar wind experienced by Earth. Without a powerful magnetic field, a planet has limited protection against such relentless exposure. Atmospheric escape becomes increasingly difficult to prevent. As a result, scientists continue debating what survives there today. Perhaps oceans endured beneath a resilient atmosphere. Perhaps water vanished long ago. Perhaps the surface became a barren landscape stripped by billions of years of radiation and stellar storms. That uncertainty gives Proxima Centauri b its unusual significance. The nearest potentially Earth-like world ever discovered may also demonstrate how fragile habitability can be. Distance alone is not enough. Sometimes the closest destination reveals just how demanding the conditions for a truly welcoming planet can be. Imagine removing everything that makes a giant planet look giant. Strip away the immense layers of hydrogen and helium, peel back the swollen atmosphere, and leave only the hidden center behind. Far from being a thought experiment, that possibility may already exist in the form of TOI 849b, a remarkable world discovered in 2020 by the Transiting Exoplanet Survey satellite. The planet resides about 730 light-years from Earth. Its measurements immediately attracted attention. TOI 849b possesses roughly 40 times Earth's mass, placing it in the same general range as Neptune and some smaller gas giants. Yet its radius is only about 3.4 times that of Earth. Something does not fit. Planets with that much mass are expected to carry enormous envelopes of lightweight gas. Standard formation models predict thick outer layers of hydrogen and helium surrounding a dense interior. But TOI 849b appears to have almost none of that material. The result is extraordinary density. Astronomers quickly realized they might be observing an object that occupies a strangely empty region of planetary possibilities. Worlds this massive rarely appear so compact. The planet circles its star once every 18 hours, racing around its orbit in less than a single Earth day. Such proximity exposes it to intense stellar radiation and extreme environmental stress. But the mystery runs deeper. One explanation suggests TOI 849b began life as a genuine gas giant. Over time, powerful radiation from its nearby star may have blasted away the outer atmosphere. Another possibility involves a catastrophic collision that stripped the planet of its gaseous layers, exposing what had once been buried far below. A different idea remains on the table. Perhaps the planet never completed its transformation into a gas giant. During formation, growing worlds gather surrounding gas from the disk of material orbiting a young star. If that process stopped unexpectedly, TOI 849b may have remained a failed giant, accumulating enormous mass while never acquiring the vast envelope expected of such a world. Either scenario leads us somewhere remarkable. If this object truly represents the uncovered core of a former giant planet, then we are observing a region normally hidden beneath thousands of kilometers, which is about 621 miles, of gas and cloud. The deep interiors of planets like Jupiter and Saturn remain inaccessible to direct observation. TOI 849b may offer a rare glimpse into material that usually remains concealed forever. Conditions there would be profoundly alien. Estimated temperatures approach 1,500 degrees Celsius, or 2,732 degrees Fahrenheit. Heavy elements likely dominate the composition. Metals, silicates, and compressed planetary matter may form much of the world beneath whatever atmosphere remains. But beyond the measurements lies a larger significance. Most planets show us their surfaces, their clouds, or their atmospheres. TOI 849b may be showing us something else entirely. It may be revealing the underlying structure of a giant world, the dense framework that normally supports an entire planetary kingdom above it. In that sense, this distant object resembles a giant planet turned inside out, exposing secrets that were never meant to be seen. Some discoveries arrive with years of follow-up observations, growing richer as telescopes return again and again. Others appear only once. A brief alignment occurs, a signal emerges, and then the opportunity vanishes forever. That is the story of Ogle 2016 blog 1195 LB, one of the most distant and elusive worlds ever identified. Its discovery came in 2017 through gravitational microlensing, a technique that depends on gravity's ability to bend light. When a foreground star passes almost perfectly in front of a more distant background star, the foreground object's gravity acts like a natural lens. The background starlight briefly brightens. If a planet accompanies the foreground star, it leaves a subtle signature within that brightening pattern. For a short moment, the planet revealed itself. Then it disappeared again. The world lies roughly 13,000 light-years from Earth, near the crowded central regions of the Milky Way. Unlike many exoplanets studied through repeated transits or ongoing measurements, This planet offered astronomers only a fleeting glimpse. The cosmic alignment responsible for its detection will never occur again in exactly the same way. Yet even that brief encounter revealed something remarkable. The planet appears to possess about 1.4 times Earth's mass, making it a rocky world comparable in scale to our own. But similarity ends there. It circles an exceptionally dim object, either a very low mass red dwarf star or perhaps a brown dwarf, a failed star that never accumulated enough mass to sustain hydrogen fusion in its core. Very little warmth reaches the planet. As a result, estimated surface temperatures approach negative 220 degrees Celsius or negative 364 degrees Fahrenheit. At such temperatures, water freezes completely. Carbon dioxide freezes, methane freezes. Materials that behave as gases on Earth become rigid solids under such relentless cold. The landscape would be motionless. Ice would dominate every horizon. Any atmosphere that once existed could collapse onto the surface as frozen deposits. Chemical activity would slow dramatically. Energy from the faint host object contributes almost nothing compared with the warmth received by Earth from the Sunday. But the planet's significance extends beyond its climate. Ogle, 2016, blog 1195, LB belongs to a population that may be extraordinarily common throughout the galaxy. These distant frozen worlds are difficult to detect because they emit little light and often orbit stars that are themselves barely visible. Most remain hidden from us. Microlensing occasionally changes that. The technique allows astronomers to find planets at distances unreachable through many other methods. Yet it carries a limitation. Once the alignment ends, detailed follow-up becomes nearly impossible. We learn enough to know the planet exists, estimate its mass, and infer broad characteristics. Much else remains unknown. So this world occupies a curious place in our growing catalog of exoplanets. We can point toward its location, we can describe its likely cold and its tiny star. But beyond those sparse details stretches uncertainty. A distant planet emerged from darkness for a single instant through a trick of gravity and light, leaving behind just enough evidence to remind us how many unseen worlds may still wander beyond our reach. A turning point arrived in January of 2011. After months of searching through immense volumes of starlight data, the Kepler Space Telescope confirmed something astronomers had hoped to find for decades. A rocky planet beyond our solar system had finally emerged from the numbers. Its name was Kepler 10b. The world circles a star roughly 564 light-years away in the constellation Draco. Compared with many giant exoplanets discovered before it, Kepler 10b seemed modest in size. Its radius measures about 1.47 times that of Earth, while its mass reaches roughly 3.7 Earth masses. Those numbers immediately told researchers something important. This was stone and metal, a genuine terrestrial planet. Yet the resemblance to Earth ends almost immediately. Kepler 10b races around its star once every 20 hours. The planet orbits approximately 20 times closer to its star than Mercury orbits the Sunday. Such proximity transforms the entire nature of the world. Heat dominates everything. Estimated dayside temperatures exceed 1,400 degrees Celsius or 2,552 degrees Fahrenheit. At such extremes, familiar geology begins to lose meaning. Rocks do not remain solid. Minerals melt. Entire landscapes may flow like liquid. Many planetary scientists believe the dayside is covered by a vast magma ocean. Molten rock could stretch across the illuminated hemisphere, glowing beneath relentless stellar radiation. Mountains, if they exist at all, would struggle to remain permanent features. The surface itself may be constantly reshaped by intense thermal forces, but the planet presents another layer of intrigue. Its density appears remarkably high, around 8.8 grams per cubic centimeter, compared with Earth's 5.5 grams per cubic centimeter. That figure suggests an unusually large iron core. Some models indicate that metal may dominate much of the planet's interior structure. In a sense, Kepler 10b could be viewed as a giant furnace wrapped around an enormous metallic heart. The planet is also likely tidally locked. Tidal locking occurs when a world's rotation becomes synchronized with its orbit, causing the same hemisphere to face the star continuously. One side experiences perpetual daylight, the other remains turned away. That arrangement creates dramatic contrasts. The day side endures constant heating. The night side may be substantially cooler. Between them lies a boundary region where temperatures change rapidly across relatively short distances. Such conditions could drive unusual circulation patterns in any thin atmosphere or vaporized rock environment that exists above the surface. But beyond its physical characteristics, Kepler 10b occupies a special place in astronomical history. The Kepler mission was designed to search for planets resembling Earth. Scientists hoped it would reveal small, rocky worlds hidden among the stars. When the telescope achieved its first confirmed rocky planet, the discovery validated the mission's approach and demonstrated that terrestrial planets could indeed be detected across interstellar distances. There was a certain irony in that success. The first rocky world confirmed by the Kepler Space Telescope was not a blue ocean planet, nor a temperate landscape. Instead, it was a blazing realm of molten stone and metal. Yet by finding something so hostile, astronomers gained confidence that gentler worlds might also be waiting to be discovered among the countless stars beyond our own. Picture a horizon where sunrise is never quite the same twice. One star climbs first, another follows behind. Their positions shift from week to week, weaving changing patterns across the sky. For generations, such a world belonged to imagination. Then, astronomers found one. Kepler 16b became the first confirmed circumbinary planet, a planet orbiting two stars at once. Located about 245 light-years away in the constellation Cygnus, it demonstrated that planetary systems could emerge in environments once considered too complicated for stable formation. The discovery settled a long debate. For decades, scientists wondered whether planets could grow within the constantly changing gravity of binary stars. Dust and gas surrounding two stars experience shifting gravitational forces. Theoretical models suggested planet formation might be difficult, perhaps even impossible in some cases. But Kepler 16b showed nature had already solved the problem. The planet itself resembles a gas giant. Its size is close to Saturn's, although its mass is only about one-third that of Jupiter. Every 229 Earth days, it completes a journey around its stellar pair. Meanwhile, the two stars circle one another every 41 days, creating an ever-changing celestial dance. From the planet's perspective, the sky would never settle into a predictable routine. Sometimes the two suns would appear near each other. At other times, they would spread far apart across the heavens. Their combined brightness would rise and fall as their orbital positions changed. Light would remain dynamic, constantly reshaped by motion. But the famous image of twin sunsets hides a harsher reality. Kepler 16b orbits near the outer edge of the system's habitable zone. Estimated temperatures range from roughly negative 73 degrees Celsius or negative 100 degrees Fahrenheit to negative 101 degrees Celsius or negative 150 degrees Fahrenheit. Such conditions make the planet a frozen gas giant rather than a place where familiar forms of life could flourish. Another challenge emerges from gravity itself. The pull of two stars never remains perfectly constant. Their motion continually alters the gravitational environment around them. For a large gas giant, long term stability is possible. Smaller rocky planets placed in certain regions may face a far more complicated situation. Their orbits could be disturbed over time as the gravitational influence shifts. This creates the first problem. The second involves light and heat. Imagine standing on a hypothetical moon orbiting Kepler 16b. Daylight would fluctuate in intricate ways as the stars moved around one another. Heating patterns could vary dramatically. Eclipses would occur frequently. At times, one star would pass in front of the other, reducing the amount of energy reaching the landscape below. Yet these complications make the system more fascinating, not less. Each orbital cycle reveals another example of how flexible planetary formation can be. Kepler 16b expanded our understanding of where planets may exist and how they survive. The discovery showed that even within a gravitational environment that seems chaotic from afar, worlds can still emerge, settle into stable paths, and continue their journeys beneath the glow of two suns instead of one. Direction seems like one of the simplest properties a planetary system can possess. A star forms from a rotating cloud of gas. A disk develops around it. Planets emerge from that same spinning material. We would expect everything to move together, following the same broad pattern established at birth. Most of the time, that expectation is correct. In our own solar system, every major planet travels around the Sun in the same direction that the Sun rotates. This shared motion preserves a record of the ancient disk from which the planets formed billions of years ago. Order appears built into the architecture itself, but some distant worlds tell a different story. Astronomers have discovered a small yet important group of giant planets whose orbits are dramatically misaligned with their stars. A few go even further. They travel in the opposite direction altogether, tracing retrograde orbits that move against the spin of their host stars. One of the earliest and most influential examples was HAT P7b. Observations revealed that its orbit was severely tilted relative to its star's rotation. The finding challenged long held assumptions about how planetary systems evolve after formation. Soon, another discovery deepened the mystery. In 2009, astronomers confirmed that WASP 17b follows a retrograde orbit. It became the first known exoplanet clearly observed moving backward relative to the rotation of its star. The result was startling because it implied that the planet's current path could not represent its original configuration. Something had changed it. But reversing a giant planet's orbit requires immense gravitational influence. One leading explanation involves the Kozai leadoff mechanism. This process occurs when a distant companion, star or planet, gradually perturbs another world's orbit. Over millions of years, repeated gravitational nudges can increase orbital tilt until the path becomes highly inclined or even completely flipped. Another possibility is even more chaotic. Planet scattering occurs when multiple giant planets interact through close gravitational encounters. One world may be ejected entirely from the system. Another may survive but emerge on a radically altered trajectory. The orderly arrangement present during formation can be transformed into something far more complex. The evidence suggests these events are not rare accidents. WASP 17b itself carries additional clues. The planet is enormously inflated, measuring roughly twice Jupiter's diameter, despite possessing only about half of Jupiter's mass. Its unusual structure hints at a turbulent history, one that may be connected to the same gravitational processes that altered its orbit. What we observe today is merely the aftermath. The planets now circle their stars with apparent stability. Their paths repeat predictably. Their motions can be calculated years into the future. Yet those calm orbits preserve traces of ancient upheaval that unfolded long before any telescope existed to witness it. But perhaps the broader lesson reaches beyond these individual worlds. Retrograde planets reveal that planetary systems are not always orderly machines assembled once and left unchanged. They can become arenas of gravitational conflict where giant worlds pull, scatter, tilt, and reshape one another across immense spans of time. When we encounter a planet orbiting backward, we are seeing the surviving record of a violent chapter written deep within the history of an alien system. Far beyond Neptune, where sunlight weakens into a distant glow and orbital journeys stretch across immense spans of time, a puzzle began to emerge from the motions of a handful of tiny worlds. The objects themselves were unremarkable at first glance. Their trajectories were not. In 2016, California Institute of Technology astronomers Konstantin Batygin and Mike Brown published a remarkable proposal. They argued that several distant trans-Neptunian objects, small icy bodies orbiting beyond Neptune, appeared to share an unusual orbital alignment. The clustering seemed difficult to explain through chance alone. The pattern drew attention. 6 of these remote objects followed elongated paths that pointed in roughly the same direction. Statistical studies suggested such an arrangement should be rare if no larger gravitational influence existed nearby. Something unseen appeared to be shaping the architecture of the outer solar system. But the proposed explanation was extraordinary. According to the hypothesis, a massive undiscovered planet may be orbiting far beyond the known giants. Estimates place its mass between roughly 5 and 10 times that of Earth. Its average distance from the Sun could range from 400 astronomical units to 800 astronomical units. That equals about 59,838 million kilometers, which is about 37,181 million miles, to 119,677 million kilometers, which is about 74,362 million miles. At such distances, movement becomes incredibly slow. A single orbit around the Sun might require between 10,000 and 20,000 Earth years. Entire civilizations could rise and disappear before the planet completed even a fraction of its journey. Finding such a world would be difficult. Sunlight fades dramatically with distance. A planet located hundreds of astronomical units away would reflect very little light toward Earth. Even large telescopes could struggle to detect it against the vast darkness of the outer solar system. This challenge helps explain why a substantial object might remain undiscovered despite decades of observation. The proposed planet would also be intensely cold. Current estimates suggest temperatures near -226 degrees Celsius or -375 degrees Fahrenheit. Under such conditions, the world would receive only a tiny fraction of the energy reaching Earth. It would exist in an environment barely warmer than interstellar space itself. Its nature remains uncertain. Planet 9 could be a super-Earth, a planet larger than Earth but smaller than Neptune. It might instead resemble a mini Neptune, a class of world frequently observed around other stars. Curiously, such planets are common throughout the galaxy, yet no confirmed example exists within our own planetary family. But not every scientist agrees that a hidden giant is required. Some researchers suggest the observed orbital clustering could result from many smaller, undiscovered bodies acting together. Others question whether observational biases may influence the apparent pattern. The debate remains active and unresolved. New observations may eventually provide an answer. The Vera C. Rubin Observatory and its legacy survey of space and time were designed to repeatedly scan the sky with unprecedented depth and coverage. If Planet 9 exists, future surveys may finally reveal it. Until then, an intriguing possibility remains. Somewhere beyond the familiar planets, beyond the icy frontier we have already mapped, a world larger than Earth may be tracing a path through darkness, present yet unseen, waiting at the edge of what we currently know. Imagine a coastline without water, a horizon without soil. Beneath you, an entire hemisphere glows with molten rock, its surface moving like a vast incandescent sea. Across the galaxy, astronomers have identified a growing class of planets where such landscapes may be completely ordinary. These are lava planets. Rather than focusing on a single world, this category brings together several extreme planets, including Korot 7b, Kepler 10b, and other scorched bodies orbiting perilously close to their stars. Their defining feature is simple yet astonishing. Rock itself becomes liquid. The temperatures involved are immense. Dayside conditions can range from roughly 1,500 degrees Celsius or 2,732 degrees Fahrenheit to 3,000 degrees Celsius or 5,432 degrees Fahrenheit. Such heat rivals industrial furnaces and approaches temperatures found in some stellar environments. Under these conditions, familiar geology begins to behave in unfamiliar ways. Mountains cannot remain stable. Solid rock melts, minerals separate, entire regions may transform into oceans of magma hundreds of kilometers deep, which is about 124 miles. Instead of continents drifting through water, liquid stone dominates the landscape. But the surface is only part of the story. At these temperatures, elements normally locked inside rocks begin to vaporize directly into the air. Sodium enters the atmosphere, potassium follows. Silicon, oxygen, and iron can also evaporate from the molten ground. The result is a rock vapor atmosphere, a thin envelope composed not of water vapor or nitrogen, but of minerals lifted from the planet itself. Everything works differently there. On Earth, atmospheric chemistry is shaped by oceans, life, and weather systems. Lava planets operate under another set of rules. Their atmospheres are controlled primarily by geology. The surface feeds the sky, and the sky returns material to the surface. Some models suggest an even stranger effect. A thermal inversion occurs when temperatures increase with altitude rather than decrease. Certain mineral vapors absorb stellar energy efficiently, potentially creating atmospheric layers that grow hotter as you move upward. This reverses the pattern we experience in Earth's lower atmosphere. Meanwhile, many lava planets are tidally locked. One hemisphere permanently faces the star. The opposite hemisphere remains turned away. On the day side, rivers of magma may flow across glowing plains. On the night side, temperatures can fall enough for rock to solidify. A single world may contain both liquid oceans of stone and vast frozen volcanic crusts. but gravity continues shaping the landscape. Some researchers predict lava tides, enormous rises and falls within molten oceans driven by the nearby star's gravitational pull. The process resembles the way our moon influences Earth's oceans, although here the moving material is liquid rock rather than water. Volcanic activity may never truly stop. Instead of isolated eruptions, outgassing could occur across the entire planet. Mineral vapor would continuously escape from molten regions, feeding the atmosphere in a cycle powered by relentless heat. If you could somehow hover above such a world, the view would feel almost unreal. Red-orange currents would stretch beyond the horizon. No blue sky would appear overhead. No oceans would shimmer. Only flowing stone, radiant heat, and a planet reshaped by temperatures that push rock itself into motion. Across much of the galaxy, sunrise may happen only once. A planet forms around its star, settles into a close orbit, and over immense spans of time, gravity begins reshaping its rotation. Each pass raises subtle tidal bulges within the planet. Energy dissipates. Rotation slows. Eventually, the process reaches equilibrium. One hemisphere faces the star forever, while the opposite hemisphere remains turned toward space. The transformation is remarkably common. For planets orbiting close to dim stars, especially red dwarfs, tidal locking is often the expected outcome rather than an exception. Many of the worlds we have explored likely exist under this arrangement. Their skies never change in the way ours do. On the day side, the star never moves. At the center of that hemisphere, light pours down continuously. Temperatures can climb to extraordinary levels. Far away on the night side, no dawn ever arrives. The star remains permanently hidden below the horizon. Heat escapes into space, and cold deepens year after year. But between those extremes lies a narrow frontier. Astronomers call it the terminator line, the permanent boundary separating day from night. Imagine standing there. The star would hover forever near the horizon, neither rising nor setting. Shadows would stretch endlessly across the landscape. Time itself might feel different. Some astrobiologists consider this region especially intriguing. The blazing day side may be too hot, the frozen night side may be too cold, yet the twilight belt between them could receive moderate energy for billions of years. Under favorable conditions, temperatures there might allow liquid water to persist. Everything depends on the atmosphere. Air heated beneath perpetual daylight expands and rises. It then flows toward the colder hemisphere. There it cools, sinks, and begins the journey back again. Instead of many circulation cells like those on Earth, a tidally locked planet may develop one enormous global convection pattern, a planetary engine moving heat from one side to the other. But atmospheric transport has limits. If the night side becomes sufficiently cold, gases may begin condensing directly onto the surface. Carbon dioxide could freeze. Other atmospheric components might follow. Snow would not fall from water clouds, but from the atmosphere itself. Over immense timescales, the dark hemisphere could gradually collect frozen gases until much of the atmosphere disappears. This process is known as atmospheric collapse. Whether collapse occurs depends on a delicate balance involving atmospheric composition, surface pressure, and wind efficiency. A slightly denser atmosphere may survive, a thinner one may not. Small differences can reshape an entire world. We see related gravitational effects closer to home. Earth's moon is tidally locked, which is why the same face always looks toward us. Mercury follows a different arrangement called a 3 to 2 spin orbit resonance, rotating 3 times for every 2 trips around the Sunday. The broader lesson is striking. The most abundant stars in the galaxy are red dwarfs, and many planets orbiting them are likely tidally locked. That means one of the most common planetary environments in existence may be permanently divided between scorching daylight and enduring darkness, with only a slender ring of twilight connecting the two. After crossing so many strange horizons, it becomes worth pausing on a simple idea. What do we actually mean when we call a planet deadly? The answer seems obvious at first. A world of molten rock is deadly. A frozen wasteland is deadly. A planet battered by radiation or crushed beneath immense pressure is deadly. Yet each of those judgments begins with a hidden assumption. We are measuring those places against ourselves, against human biology. Every world we have visited would kill a human being quickly. Some would do so in seconds. Others would take longer. But that tells us something about our requirements, not necessarily about the planets themselves. Life on Earth depends upon a very specific combination of conditions. We need liquid water. We need temperatures within a narrow range. We need an atmosphere rich in oxygen. We need chemistry built around carbon. Remove any one of those ingredients, and survival becomes difficult. But Earth did not always provide them. Travel back to the Archean Eon more than 3 billion years ago, and you would find a planet profoundly different from the one beneath our feet today. The atmosphere contained methane, ammonia, and carbon dioxide. Free oxygen was almost absent. Oceans existed, yet the air itself would have been toxic to modern humans. A survey searching for habitable worlds might have rejected Earth entirely. Then came one of the most transformative events in planetary history. Around 2.4 billion years ago, microscopic organisms began releasing oxygen into the environment. Today, we celebrate oxygen as the foundation of complex life. At the time, it was a catastrophe. For countless anaerobic organisms, meaning life forms that lived without oxygen, this new gas acted as a poison. The Great Oxidation Event triggered the first known mass extinction. Entire ecosystems collapsed. A planetary condition that supports us today once threatened much of the life already present. But Earth was not finished reshaping itself. Across hundreds of millions of years, our planet experienced repeated biological crises. At least 5 major mass extinctions transformed the course of evolution. During the Permian-Triassic extinction, approximately 252 million years ago, an estimated 96% of marine species disappeared. Around 70% of land, vertebrate species vanished as well. For a time, Earth became one of the deadliest places known to the creatures living upon it. That realization changes the meaning of habitability. What we call habitable is really a narrow biological preference. It reflects our chemistry, our physiology, and our evolutionary history. Another form of life might draw the boundaries differently. Some researchers have explored alternative possibilities. Silicon-based biology has been proposed as a theoretical counterpart to carbon-based life. Other ideas imagine ammonia serving as a solvent where water cannot. Certain microorganisms on Earth already use sulfur compounds in environments once thought impossible to inhabit. Perhaps those possibilities remain rare. Perhaps they do not exist at all. But they remind us to be careful. When we describe a planet as deadly, we are often describing its relationship to us. The universe does not divide worlds into welcoming and hostile categories. It simply produces environments. Some fit our needs, others do not. Seen from that perspective, the cosmos feels less cruel than indifferent, and the word deadly begins to reveal as much about humanity as it does about the planets themselves. For decades, one idea guided much of the search for life beyond Earth. Find the right distance from a star, and you might find a living world. The concept seemed straightforward. Astronomers called it the habitable zone, the region around a star where temperatures could allow liquid water to exist on a rocky planet's surface. Since water is essential to every known organism on Earth, this became a natural starting point, a useful first filter. Yet, as discoveries accumulated, the picture became more complicated. Distance alone could not determine whether a planet was truly hospitable. Two worlds receiving similar amounts of starlight might experience completely different fates. Atmospheres matter enormously. Magnetic fields matter. Geological activity matters. Ultraviolet radiation matters. Stellar flares matter. The ability to retain air over billions of years matters. One by one, factors once considered secondary moved toward the center of the discussion. The habitable zone began shrinking. Consider the red dwarf stars that dominate our galaxy. These small stars make up roughly 70 to 75% of all stars in the Milky Way. At first glance, they appeared promising because they are abundant and often host planets. But their habitable zones lie extremely close to the star. That proximity introduces new problems. Tidal locking becomes likely. Powerful flares become harder to avoid. Stellar winds can batter atmospheres for immense spans of time. Even a planet sitting within the traditional habitable zone may gradually lose the very conditions that made it attractive. The label remains technically correct. The reality may not be. Researchers eventually expanded their perspective beyond individual stars. This led to the idea of a galactic habitable zone, a broader framework suggesting that location within the galaxy itself influences long-term habitability. Move too close to the galactic center, and the environment grows crowded and energetic. Radiation levels increase. Stellar encounters become more common. Move too far outward, and heavy elements become less abundant. Without those elements, building rocky planets becomes more difficult. Position matters at every scale. Our own solar system appears to occupy a favorable region. We reside neither deep within the crowded galactic core nor far beyond the richer stellar neighborhoods. The ingredients for rocky worlds were available, while nearby cosmic hazards remained relatively limited. Some scientists view this as significant. In 2000, Peter Ward and Donald Brownlee proposed the rare Earth hypothesis. Their arguments suggested that complex life may require an unusually specific combination of conditions, many of which must remain stable for billions of years. Under that view, Earth-like biospheres could be extraordinarily uncommon. But another perspective remains equally compelling. The observable universe contains more than 100 billion galaxies. Each galaxy contains hundreds of billions of stars. The numbers become almost impossible to grasp. Even tiny probabilities can produce vast outcomes. As we reflect on the worlds explored throughout this journey, a pattern emerges. We encountered planets scorched by heat, stripped by radiation, frozen beyond imagination, battered by gravity, or trapped beneath crushing pressures. Each discovery revealed another way for a planet to become inhospitable. Yet those same discoveries also reveal abundance. The universe produces worlds endlessly. Most appear hostile to life as we know it. But somewhere among those countless planets, rare combinations of circumstances may still unfold, creating places where biology finds a foothold and endures. After wandering across worlds of glass storms, iron rain, frozen darkness, and molten horizons, we arrive somewhere unexpectedly familiar. we arrive back at Earth. The contrast changes everything. Each extreme planet acts like a natural experiment, revealing what happens when a single condition is pushed beyond ordinary limits. By studying those distant worlds, we begin to understand why our own planet functions the way it does. Consider the atmosphere first. On the world known as HD 189733b, winds race through an environment so violent that glass particles can be driven sideways through the sky. Atmospheric circulation there reaches extraordinary extremes because the planet rotates under conditions far removed from anything we experience. Earth behaves differently. Our rotation rate and moderate solar heating help distribute energy more evenly across the globe. Storms still form, winds still blow, yet the atmosphere remains remarkably stable compared with many planets beyond our solar system. Another lesson comes from WASP 76b. There, temperatures become so intense that iron can vaporize into the atmosphere before condensing and falling elsewhere. The planet orbits astonishingly close to its star. Distance alone transformed an ordinary planetary ingredient into weather. A small change matters. Mercury circles our Sun at roughly 58 million kilometers, which is about 36 million miles. Even that scorching world remains far enough away to avoid becoming an iron rain planet. Orbital position shapes everything that follows. Far beyond the warmth of stars, rogue planets offer another perspective. These wandering worlds drift through interstellar space without a parent star. Their existence reminds us that planetary systems are not always stable. Some worlds get lost. Our own system appears unusually well organized. The giant outer planets help regulate gravitational interactions over immense stretches of time. Their presence may have reduced the chances of Earth being scattered into deep space long ago. The lava planets tell an even more personal story. Today we walk across solid continents and oceans, but about 4.5 billion years ago, Earth itself was a magma ocean world. Impacts arrived constantly. Vast regions glowed with molten rock. The difference between Earth and many lava planets is not category, it is timing. We changed. Tidally locked planets reveal another fortunate circumstance. Many exoplanets keep one hemisphere facing their star forever. Earth rotates once every 24 hours, allowing heat to circulate across the surface instead of accumulating endlessly on one side. Balance emerges from motion. Deep beneath our feet, a liquid iron outer core generates a magnetic field. This invisible shield deflects much of the solar wind streaming outward from the sunday. Without that protection, atmospheric loss could gradually reshape our world, much as scientists suspect occurred on Mars. Even the moon contributes. Its gravitational influence helps stabilize Earth's axial tilt near 23.5 degrees. Without that stabilizing effect, long-term climate variations might become dramatically more severe. Jupiter plays a role as well. Across billions of years, its enormous gravity has altered the paths of countless comets and asteroids. Some still reached the inner solar system, but many others were diverted elsewhere. Taken together, these examples reveal a deeper pattern. Every deadly planet shows a different path nature can follow. Each one highlights a condition that shifted too far, lasted too long, or unfolded differently. And through those distant extremes, we discover how many circumstances had to align before Earth became home. At some point during a journey like this, the statistics begin to feel different. Numbers stop behaving like numbers. They become landscapes. We have crossed worlds where iron falls from the sky, We have drifted above oceans of molten stone. We have stood beside planets, wandering alone between the stars. Yet, after all that distance and variety, one pattern remains stubbornly consistent. None of them are home. Not one offers a breathable atmosphere. Not one provides a familiar shoreline. Not one allows a human being to rest beneath an open sky and wait for morning. The realization settles slowly. For decades, scientists have wrestled with a puzzle known as the Fermi paradox. It asks a deceptively simple question. If the universe contains so many stars and planets, where is everybody? The question grows heavier tonight. Modern estimates suggest that the observable universe contains more than 100 billion galaxies. Each galaxy contains hundreds of billions of stars. Around many of those stars orbit planets. The numbers become almost impossible to picture, but abundance alone guarantees nothing. Again and again, the worlds we have encountered reveal environments shaped by crushing pressure, lethal radiation, extreme cold, relentless heat, atmospheric collapse, or gravitational instability. Perhaps the mystery is not why intelligent life appears scarce. Perhaps the mystery is that it emerged anywhere at all. That possibility reaches into another famous idea. The Drake equation attempts to estimate how many communicative civilizations might exist. One of its most uncertain factors concerns the moment life first appears. How often does chemistry become biology? How often does a lifeless world begin to replicate, evolve, and adapt? No one knows. Every hostile planet adds another reminder that suitable conditions may be extraordinarily difficult to maintain across immense stretches of time. Complex life requires persistence. It requires stability. It requires countless circumstances working together for millions and billions of years. Yet beneath those scientific questions rests something more personal. What does it mean that you exist during such a moment? Among all the worlds we have visited, you are listening from one that produced oceans, forests, clouds, language, memory, curiosity, and the ability to wonder about distant suns. That fact can feel almost improbable. Meanwhile, far beyond the planets, two small spacecraft continue their journey. Voyager 1 and Voyager 2 move through interstellar space even now. Each carries a golden record containing greetings in 55 languages, music, sounds, and images from Earth. They drift outward year after year, carrying fragments of our world into the darkness. Voyager 1 now travels more than 24 billion kilometers, which is about 14.9 billion miles, from Earth. The space surrounding it is the same vast expanse that envelops countless distant planets. An image from that journey inspired one of astronomy's most enduring reflections. When Carl Sagan looked at a photograph of Earth taken from roughly 6 billion kilometers, which is about 3.7 billion miles, away, he saw only a tiny point suspended in a scattered sunbeam. After everything we have seen, that tiny point appears differently. Every deadly world strengthens the same conclusion. Earth is neither the largest world nor the most powerful. Yet it remains astonishingly rare in our experience, a fragile island of life, surrounded by an ocean of cosmic possibility, and perhaps by a great, enduring silence. Far enough away, Earth stops looking like a place. The mountains disappear first, then the oceans, then the clouds. Distance smooths every familiar detail until our world becomes a single point suspended in darkness, one small sphere among countless others scattered across the galaxy. From that perspective, something becomes easier to see. Right now, somewhere in the constellation Vulpecula, Glass is racing sideways through an alien atmosphere at thousands of miles per hour. Entire weather systems move across a world unlike anything found in our own solar system. No one stands beneath those skies. Elsewhere, on WASP 76b, iron vapor cools, condenses, and falls through distant clouds. Metal drifts downward through an atmosphere heated beyond ordinary imagination. No hand has touched it. Beyond the glow of stars, rogue planets continue their endless journeys. They wander through interstellar darkness, without sunrises, without seasons, without a home star to circle. Some began that voyage before Earth formed from dust around a young Sunday. They are still traveling. Every world we have visited tonight is real. None belong to fiction. They exist at this very moment, carrying on their strange histories whether anyone observes them or not. Vast distances separate us from them, yet they remain part of the same universe, the same cosmic story. But here, something different happened. On this small planet, temperatures settled into a narrow range. Water remained liquid. The atmosphere endured. Chemistry became biology, and biology became awareness. Over immense spans of time, living things learned to look upward. Eventually, they learned to ask questions. That outcome can feel ordinary because it surrounds us every day. But when placed beside the countless hostile worlds scattered through space, its rarity becomes harder to ignore. Consider the scale. Current estimates suggest the observable universe may contain roughly 2 trillion galaxies. Within them are hundreds of billions of stars, repeated again and again across distances almost beyond comprehension. Around many of those stars orbit planets of every imaginable kind. The numbers are overwhelming, yet among all the worlds known so far, only one is confirmed to host a mind capable of wondering about the rest. Only one has revealed forests, oceans, civilizations, music, memory, mathematics, stories, and the ability to contemplate existence itself. As far as we currently know, that world is Earth. Perhaps other minds exist elsewhere. Perhaps distant civilizations are looking outward beneath unfamiliar skies. Or perhaps awareness is exceedingly rare, a fragile phenomenon appearing only occasionally amid vast stretches of lifeless space. For now, we do not know. What we do know is simpler. The sky is crowded with worlds. Some burn, some freeze, some wander alone, some circle multiple stars, some carry storms beyond anything our planet has ever experienced. And still, after everything we have seen, the most remarkable world remains the one beneath your feet. So the silence between the stars remains. Not empty, perhaps, not forever unexplained, just vast enough to remind us how extraordinary it is that, on one small world, orbiting one ordinary star, the universe became aware of itself and paused long enough to listen.